Hello everyone. Last lecture we have learned about startups of Envy, the setting preferences, opening and saving images, and display management. The content of this lecture will be a little more troublesome or complex. In this lecture, we will learn about how to perform the geometric corrections using Envy. Inevitably, the original satellite image is usually geometrically deformed. This kind of geometrical deformation can generally be divided into two categories, two types, named systematic and unsystematic. For the first one, the systematic deformation or the systematic error is usually called by the sensor, which is regular and predictable. It can be corrected by the corresponding sensor model. Usually, the satellite ground receiving stations or the agencies for remote sensing data receiving, processing, and distribution. This agency have completed the correction works for the systematic deformations. Therefore, as users, we usually do not need to deal with the system errors, but for the non-systematic geometric deformation, it is irregular and caused by a series of reasons, such as the instability of flight altitude, or the change of the height, the speed of the satellite, or the curvature and the rotation of the Earth, and the air refractions, etc. The purpose of geometric correction is to eliminate the geometric deformation caused by these non-system factors. In addition, during the geometric correction process, the special coordinates are assigned to the image data. Thus, the geometric correction include correcting for geometric directions due to sensor and Earth geometric variations, and converting of the data to a real-world coordinate, such as longitude and latitude, coordinates on the Earth's surface. Therefore, the image data after geometrical corrections usually has a correct coordinate and can be displayed to the correct position on the Earth. Okay. What I said is somewhat theoretical and complex. However, for any image, there are only two possibilities. That is geometrical corrected and no geometrical corrected. In most situations, as users of remote sensing data, we can choose to download the higher level data, which usually have been geometrically corrected, such as the MODIS level 3 or level 4 data, or the Landsat data, such as this is the official website of MODIS. We can find the official provide level 1 raw data and high level data products, such as the atmosphere products, the land products, and the ocean products. All of these products is high level. It's level 3 or level 2 data product. This data have been geometric corrected, but the level 1 data, raw radiance data, is no geometric correction. If we want to use this data, we need to do the geo correction by ourselves. Okay, this is an example. Most of us, as a data user, the remote sensing data user, in most of the situation, what we need is to download the data products produced by the official. So most of us will not use this data. But there are 4 situations we need to perform geometric correction by ourselves. The first situation is just like the MODIS. Although the official provides higher level data products, but if our research requires more primitive data, such as we need to use the raw data to avoid unnecessary errors. At this time, we need to perform geometric correction ourselves. And in our experiment data folder, we can find this one. This is raw data of MODIS. named MOD 02 1 kilometer point HDF. For this MODIS level 1 primary data product, the official only did the most basic processing and keep as much original information as possible. We can open this file from Envy by File, Open as, Optical Sensors, EOS, MODIS, and choose this data. Press Open. Okay. This is the MODIS raw data. If we open the data manager, we can find there is a lot of find be opened, such as quality, latitude, longitude, and some reflectance, and readings, several readings, and emissivity. If we open the file information, we can find all of this file. We can find this file may not have a right projection or the right geometric or the coordinate informations. In order to determine whether this data is in the correct position, we can open a global vector data for comparison, such as we open the open a world data. Here we open the countries. Okay, this is the world country boundary of each stations, each country. We can find that the land and okay, we can find this is an island. This is a big island. Maybe Philippines. We can find the boundary of the land and sea in this image is inconsistent with our standard vector data, which provide this image need to be corrected. This is the first situation. If we open the country, we can find this file, this SHP file, have the projection named Geographic Latitude, Longitude, and this is item name of this projection, and the unit is degrees. Okay, this is the first situation that we need to do the geometric corrections. And the second situation is if we need to use a data such as this 风云3 data, and the official does not provide the corresponding high-level remote sensing data product, and at this time we can only choose to do the geometric correction by ourselves, such as if we open the 风云 data, we close all of this file, and open the 风云 data by file, open as general format, and HDF file, and choose the 风云 3, choose this one. This is the H5 data, press open. If we choose to open this one, the emissivity, press this arrow and press open. The 风云 data has been opened. Okay, if we open the world data, countries, okay, we can find that these two layers is inconsistent with each other. For this one, for the country ship is correct. So we know the 风云 3 data need to be geometric corrections, because if we look the status bar, we can find the latitude the latitude is 500, maybe 600. This is definitely impossible. So this file need to be correct. Okay. This is the second situation, and the third situation is if we have two images in the same area. One of the images has been geo-corrected and has a correct coordinate information, but the other one has no projection information, or its coordinates are not accurate. In this situation, we need to do the geometric correction, such as the folder of the image to image. The first one, we open these two files, the BLDR SP.img and the BLDR TM.img. The SP means spot, and the TM means TM, which is the sensor name. this sensor is equipped on the Landsat 5 satellite. Okay, we open these two files in Envy. Firstly, we need to close all of this file, and we can choose to open this two file by drag this file to Envy interface. Okay, we press zoom to full extent. Drag is the same as the file open or the open tools in the toolbar. We can find these two images is the satellite images comes from two different sensors, but they are in one the same place, because this lake is this lake, and this city is this city. From the data manager, we can find the file information of the spot data. I find the projection name and the pixel size, which means if we know the spot file with the correct coordinates, but the TM file have no map projection. But they are in the same place. In these situations, we can use the spot images with the correct coordinates as a benchmark or as a reference to perform the geometric correction on the TM image. Okay, this is the third situation. And the last case is that if we have an images, it does not have the correct geographic coordinates, such as we open the TAN DRG data. We open this file in Envy. Firstly, we need to close the spot and TM file. Okay, this is a file, but it does not have map projection in there. So if we measured several points in the image and got their special coordinates, for example, if we took a handheld GPS and we took a GPS to measure the latitude and the longitude of several points in the picture, such as we measured the longitude and the latitude of this point, and this point, and this point, and this point, or some other point. We can use this measured point to perform geometric correction on the entire images, so that make the entire image has the correct coordinates. Okay, this is the 4 situations, we need to do the geometric corrections by ourselves. As a powerful remote sensing image processing software, it is relatively simple to use ENVI to perform image geometric corrections. Then we will learn how to use ENVI to perform this 4 different geometric correction process. For the first situation, for the level 1 raw data of models, in this situation, we need to use the method named image geometric correction based on the position information of sensors. The tool name is, we need to close this file. The full name is Georeference by Sensors. We can find this tool in the toolbox. The geometric correction, and find the georeference by sensor, and find the georeference models. Okay, first we need to open the models file. We press File, Open as Optical Sensors, and EOS models, and open the models mod02.hdf. Press Open. And we need to note that the spatial resolution of this file is 1 kilometer. And the models data is stored in HDF format. The full name of HDF is hierarchical data format, which is a self-descriptive, extensible, and self-organizing storage that can be used in most scientific research. So the HDF file is useful and powerful. ENVI support reading models level 1, level 1B, level 2, level 3, and level 4 data, including the models from MOD 02 to MOD 44. The MOD 02 is the code name of models raw data, which when the raw data is MOD 02. And for the code name of each models product can be found on this official website. After the models data be opened, we can find that ENVI automatically extract relevant datasets including georeferenced information, include the latitude and the longitude, and the quality band, and automatically calibrate modest data into the reflectance. I close this one. Reflectance and the radiance and emissivity. Now we need to select the correction tool to perform the geometrical correction. From the toolbox, we can find the geometrical correction and georeferences by sensor, and find the georeference models. We double click these tools, and this window appears. In this window, we need to select a file, which is the file need to be geometrically corrected. We can find the detailed information in the right box. We can find the name. The first one is longitude, second one is latitude, third one is quality, have only one band, and the last three one have the name is the same, but we can find some difference from the details, such as this one is the reflectance file with 22 bars, and this one is radiance, and the last one is emissivity. Okay, here we choose the reflectance file and press OK. And in this Windows, we need to set the output map projection of the data. There is a lot of map projection. Even we can create a new map projection ourselves. For the map projection, for the knowledge of projection, it is a little bit complex. Since this is not a course in cartography, so we will not talk too much about the map projection. For most of us, what we need to know is the coordinate system of the map can be divided into spherical coordinate system and plane coordinate system. Two types, spherical and plane. The most common spherical coordinate system is the World Geodetic System in 1984, which is sometimes shorted to the WGS 84, and it is a coordinate system established for the use of GPS global position system. Its unit is degrees, minutes, or the second. In the NV installation catalog, the coordinate system of all the data is WGS 18.4, such as the data, if we such as the data of countries we have opened. The space range is from 180 degree west to 180 degree east, and from the 90 degrees south to 90 degrees north. The coordinate system, this coordinate is suitable for large-scale maps, such as the countries map or the continent maps or the world maps. This is the geographic lat and long. Another type of coordinate system is the plane coordinate system. For example, the UTM, the full name is the Universal Transverse Mercator Projection, shorted to UTM coordinate system. Planar projection users the plane projection use some mathematical methods to project the spherical coordinates onto a plane. So the unit of the plane coordinate system is meters. The unit is meters, but the spherical coordinates with the unit degrees. This is the difference. And the plane coordinate system is suitable for small scales. So this is some basic knowledge about the map projection. Here we choose the geographic projections. These two projections can be choose. Which projection choose is depend on your purpose or the location of the images. For the Fengyun 3 image, is the scale of this image is large, so we choose the geographic projections, and we can choose to output the GCP file name. This is not necessary, and we just to press this one. We just choose this one, press OK. And the registration parameters, this window appears. In this window, we can change the unit. We can set some projection parameters, such as we can set the x pixel size and 1 pixel size, and the output number of x and y. In this parameters, we choose the default. If we choose to set the x and y pixel size to 0.001, and we choose this to 001, then we press enter, and the software will calculate the output x size automatically and the y size automatically. Okay, we can set the output pixel size because we know. This is the MODIS data, because we know the MODIS data is 1 kilometer. 1 kilometer, about 0.001 degrees, because the unit is degree. Because we choose the spherical projection, so the unit is degree. If we choose the UTM, the unit will become meters. So in that situation, we can set 1000, and here we can set 0.001. Okay, and we can set the background. In the default, and the background is 0. And we set output file name. We output the file to is data, correction data, MODIS and temp, MODIS size. Okay, this is the file I did the geometric correction last time, so I need to choose this one. MODIS, MODIS reflectance, geometric corrected point DAT or point IMG or something else. Set the surface name you like. Okay, set this one and press OK. And the software starts to do the geometric corrections. Okay, for the geometric correction is use a lot of time, so I used the result that I finished in the last time. This is a file be corrected by these tools, and we can find that it has a projection information, named the UTM zone and 1000 kilometers. Because this is the file I do the last time, so it is maybe different for you. If we open file, we open the world data and open the countries and press yes. Okay, this is the data. We close this one. We choose the band. We choose 3 band. Band 3, band 4, and band 2 to load data. It's a little bit slowly. Okay, this is the RGB composite data, and we put the contrast to the top layer, and we can find the land boundaries of this data have completely overlapped with the vector data. I find this is the island and this is the coastline, and this is the island of Philippines. Okay, this is the first geometric correction practice named image geometric correction based on the position information of sensors. Use this method, we can perform the geo corrections on models, on spot, Raster, or this Cosmos, AVHR. However, we can see that the data that can directly use this method is limited. For example, this toolbox does not provide a geometric correction method for Fengyun 3 dataset. So, for the data of Fengyun 3 or something or other sensors not listed in here, we need to use the other way to do the geo corrections. The second geometric correction method named image geometric correction with GLT file. Image geometric correction with GLT file. The GLT geometric correction method use the input geometric file to generate a GLT. The full name is Geolocation Lookup table. So using this lookup table, using this GLT, the software can realize the geometric correction of the data. Then we will use Fengyun 3 data to introduce this method. First, we need to open the Fengyun 3 data. And we close all of this file. We can press File, Open as, General Format, HDF4, and choose the HG5 data. Press Open. We can see the file contains various informations. because the MODIS data stored with the data with the HDF format, which is the the version 4 of HDF. So this one is the version 5, so named HDF 5 or H5. Here we select the reflectance multi-band. There is 7 band to open. So we need to choose this one and press this arrow, and we need to open some other layers. So we need to press this one and raster and create the Raster Tool. Then we need to choose the latitude and longitude. Let's say longitude. And we can find the detailed informations. We can find this is longitude and its unit is degree, and the valid range and the full value and the long name. Okay, it is powerful of this data format. We choose the latitude. Okay, this is latitude and longitude, and open rasters. And in the data manager, we can find, we open this reflectance file and the latitude and longitude. Okay, collapse. We can hide the latitude and zoom to full extent. We can find there is an island. We need to close all of this file. We can remove all, and we can load 3, 2, 1 to load data. And this is India and Sri Lanka. Okay. Next, we need to build a geolocation lookup table based on the latitude and longitude band from the toolbox named Geometric Corrections. We need to choose the Build GLT tools. Double click it. In this window, we need to input X geometric band. We need to choose X is the longitude. We need to choose the longitude and press OK. And input Y, we need to choose the latitude and press OK. And in this window is the same as the georeference by MODIS. We can set the output projection. So here we choose the geographic lat and long, and this is the input projection because this is latitude and longitude. So we need to choose this one, and the output projection. Which projection be chosen is on the purpose or the location of the study area. Here, we also choose the latitude and longitude and press OK. In the following, build a geometric lookup file parameters panel. We need to set the output pixel size and the rotation. The output pixel size and the rotation, if we choose to use the default, maybe this one, we can set as 0, and the pixel size use the default, and we can set a file name of the output GLT data. We output the file to GLT data 风云3 and temp and my GLT and press OK. Okay, you can find this is my GLT. And next, we can perform geometric correction on 风云3 data based on this GLT. From the toolbox, select geometric correction and georeference from GLT. Double click it and select the GLT file. Choose my GLT. Press OK. And select the input file need to be corrected. We can find some difference by the band. Because this is 7 band and this is 2 band. The 2 band is the latitude and longitude, so we need to choose this one with 7 band. Press OK. And in this window, select the file need to subset or the background value. We choose to the default value, so we choose set the full path of the data need to which is be geocorrected. So we store the data into 风云3 temp and name the 风云3 geocorrected from GLT point DAT. and press OK. And the data will be opened automatically. And in this situation, we can open the band 3, band 2, band 1, and load RGB composition image. And if we choose to open the world data countries, right, we can find the boundaries of this data have completely overlapped with the vector data. And this is the south part of India and the Sri Lanka island. And this is the GLT file. And this is the file before corrected. This is after geometric correction. Okay, this is the second situations that need users to do the geometrical correction. The next situation named image to image registrations, because if we have two images, the first one is right and the second one have no map projections, but they are in the same place, so we can do the geo registrations for these files. In this case, we need to choose we need to use NV Classic models. So we open the NV Classic and start up NV and NV Classic. After we open the NV Classic model, first we need to open the image data. These two image data need to be opened in NV Classic. We need to choose File, Open Image Data, and we need to find the data image geometric correction data 3 image to image, and find the spot.img and tm.img. Press open. Okay. From the available band list, this is the available band list panel. We can see the map info. This is the map info of the spot data, but the TM data have no map info. So we can use this data as a reference to do the correction on TM image. In this mapping info, we can find the projection name and the pixel size and other details about the projection informations. This dialog lists the basic map information used by NV in georeference. The image coordinates according to a reference pixel used by NV as if we right click it and press edit header, we can find the information about the data symbols and lines. Right click the map info and choose edit map information. We can edit the projection of the data, and in this panel we can see the type point. This is the first pixel as the type point, and if we know the coordinate of the pixel, if we know the first pixel because NV knows the map projection and the pixel size and the map projection parameters based on this header information and the map projection text file. It can calculate the geographic coordinates of any pixel in the image. So this is the coordinate in image, and this is the coordinate in the real world. Okay, this is how to edit or look at the details about the map info. Suppose we know that the TM file, because this file have no map projection, but suppose we know this two file is acquired in the same area, so we can use this spot data as a reference to perform geometric correction on the TM data. But before we start, let's take a brief look at the common interface of NV Classic. This is the available band list, which have the functions like the data manager in NV, in the new interface of NV, more like the data manager. This is the available band list. If this dialog has been closed, we can open it from the menu bar, the window, and choose the available band list. And This is the 3-view window of Envy. The largest one is called image window, and the lower left one is called scroll window, and this one is the zoom window. The scroll window is used to display global or overview information, and the zoom window is used to display detailed information. We can change the size of the window. Change the size. We can find the red box have been changed automatically. This is the zoom window. Find the lake. This is zoom. This is overview. The scroll window. The image window. If we double click on the image window, the cursor value will be opened. It is the same as the cursor value function of the new Envy interface. It is the same as this one, the cursor value, and this is the cursor value function. Okay. If we want to close this one, close it. In addition, there are 3 buttons on the zoom window. Their function is zoom out and zoom in, zoom out, zoom in, and open the crosshair. This is the crosshair. Help us to location to a specific pixels. Zoom in or zoom out. Okay. After having a basic understanding of the classic interface, now we will learn every step of image to image corrections. Firstly, we need to open a new display window to display another images. If we want to display the spot images, we need to choose this one because it has only one band, so we can display it into a new display. We create display 2 and load data. RGB. Oh no, we need to choose load grayscale because it is single band data. Load data, load band. Okay, the spot file have been opened. This is lake. The lake. Basic principle of image to image correction is to select several control points in 2 images to establish a transformation function. After each pixel is transformed by the function, the geometric correction of the whole image will be realized. Therefore, we need to manually select several control points first to establish the transformation functions. The specific operation method is from the NV menu bar. We need to choose the map registration and select ground control points image to image. We need to choose this one. This is the image to image registration, and the base image is the display 2, and the warped image is display 1. This is a TM file with 7 band, with 6 band needed to be correct. So the warp file, we need to choose the display 1 and press OK. In this panel, we need to choose the ground control point. We can add individual ground control points by positioning the cursor in the 2 images to the same location, and it is better to find the ground control point which is cross of the road or the cross of the river. So if we expand the zoom image, we find the ground control point. If we find this one, this is the cross of the road, and zoom in and choose this one. And in this picture, we need to find the same location. This is the same location. We need to zoom in and choose this pixel. So next step, we can press this one and point. This is the first point we selected as the ground control point. And we need to find more ground control points, such as we find the cross of this road. We find the cross of this, maybe this one, or the corner. The lake maybe expand due to the rain, so we need to we best to choose the road. We find a road there. Okay, and find this one, the road, cross over the road. This is the cross over the road, and press and point. This is the point 2. It is if it is difficult, you can do like this. In the base X field, we can type 753, and for the Y location, we can type 826, and in this one we can type the 331 and the 433, and press enter. Oh, outside of the, okay, I need to choose this one because this is the basic images. The 433. Okay, whatever. This is to tell how to enter the pixel location to add the ground control point. If it is not used, we can add the ground control point by ourselves. We can choose this little lake. Choose this one, this little lake. Zoom out, and we find this one. If this one and this one is the same location, and press endpoint, and if we find the next one, and this, okay. This road, it is difficult to find the cross of the road. Might be there. There is the cross of the road. If we choose this one, and we choose there, this is the same point and point. And we can click Show List to view the ground control point list. We can find we select for GCP. Note that the list of actual and predict point in the dialog. So we can find the base x, base y, and the warped y, and the predict x, predict y, and the error x, error y, and the IMS. If we have at least 4 points, the IMS error is reported. So if we choose another point, we can find a point match in there. Find the point. we find the point there, this is the cross, and this is the cross. Okay, and this point show the list. We can find the RMS appears. This process of selecting control points is relatively troublesome and complex. When we're choosing control points, we need to be careful. When the number of control points reach 4, when we have 4 control points, we can use the automatic prediction function to assist us in selecting points. We can click the point and automatic predict. In this way, if we choose a point in there and in the TM image, it will be located to the corresponding pixels automatically. If we choose to select this corner, if we want to choose this one, and we make we only need to fine-tune the point when selecting a control point. Choose this one and point, and if we choose to this corner, this one. Okay, if we choose this one, this is the corner. Oh, the resolution of this image is 30 meters. So for the we can choose, if we choose this one, if we choose this one, okay, if we choose this one, we need to move to there and point. After selecting some control point, we should examine the GCP list. We can find the point 5 have a large RMS, so we need to correct it by update. If we need to choose this one and press update. Maybe this one we need to delete, and the remain points have a better RMS. After selecting some data, selecting some control point, we can also sort the RMS to control the point with large errors. We can use these tools options order by error. So in this way, we can easily find the data, the GCP with large RMS. In this way, we can update it or directly delete it. We have selected some control points. The software can help us automatically select more control points. The basic principle of automatically selecting control points is that the machine will establish a sliding window and automatically select pixels with similar texture features, and we'll choose the pixels with similar DN value or texture features in the two images as the control point. For the operation, we need to choose the options and click automatically correct generated type points, and then we need to select one band to use for match the reference band. We need to choose one of the TM image band to match the spot band, because this is a single band images. So here we choose the band 2 with the wavelength of 0.56. This is the green band. We choose OK. In this window, we need to set the number of type points and the search window size, the move window size, and the error or something else. Here we set the number of type points to 50, and for the rest parameters, their function is to help the machine, who help the software to search for similar pixels more easy or more correctly. Usually we just keep the default and press OK. After that, we also the software help us to select 50 control points. Okay, it is is a wonderful tools for selecting control point. But after this, we need to open the GLT list, GCP list, and we need to delete the control point with large IMS error. So we need to choose this, press shift and choose this. First one, we need to order it and choose this point and delete. We need to delete this one. Delete. Okay. There are still many control points left. Now with the IMS less than 1 pixels. In short, the principle of control point selection is the control point should be distributed as evenly as possible in the whole picture, and not excessively clustered. The number of the control points cannot be too small, and more than 10 points is relatively better. In addition, we can save the GCP to ASC file, or we can restore the GCP from ASC file. We will test the function save GCP to ASC. Then we choose a folder, the IS data image to image temp GCP. Okay, this is the GCP I choose the last time. My GCP to open. Press OK. Okay, we can find the GCP file. This is the saved GCP file. We can open it with the text readers, such as the Notepad++ to open it. It is just ASC2 files. Okay, if you have not selected the ground control point, you can use the restore GCP from ASC. You can choose this GCP and press OK. Okay, there is a GCP I have selected. This can save your time. Finally, with this control point, we can perform the geometric correction on the image. The image can be warped, can be corrected from the displayed band, or multi-band images can be corrected all the band at once. We can use the options warp displayed band or warp the whole file. Here we choose the whole file and input warp images. Here we choose the file need to be corrected. This is a TM file and press OK. And in the registration parameters window, we need to set the warp parameters and the output extend. And we provide 3 methods to realize the geo correction. And in my opinion, the RST and polynomial and triangulation, the result generated by these 3 methods are not much different. For the subtle differences between these 3, you need to consult the NVHelp file. And here we choose the RST method. For the next one, resembling method, and we also provide 3 ways named nearest neighbor and Bio-Nano and cubic convolution. Let's briefly introduce these 3 methods. For the nearest neighbors, this resembling uses the digital value from the pixels in the original image, which is nearest to the new pixel location in the corrected images. We can find in our Word file. Okay, this is the nearest neighbors. We use this DN value to replace this one. This is the simplest method and do not alter the original value of the image, but may result in some pixels being duplicated while the other pixels may lost. This method also tends to result a disjointed or blocky image appearance, but it is simple and useful. The second one is Bio-Nano interpolation. This resembling take a weighted average of 4 pixels in the original image nearest to the new pixel location. So the averaging process alters the original pixels value and create an entirely new digital value in the output images. In short, it is the weight average of these 4 pixels. And the cubic convolution may be the weight average of the 16 pixels. So it is complex and time used for resembling. This is a brief introduction of the three resembling method. Here we choose the nearest neighbors. Then the background keep the default value. As for the output image extent, NV will automatically calculate the output range. We only need to set the output file path. Here we choose to, this is the warped TM-DAT. Okay, this name warped TM 2, maybe. Press OK. And press OK. It is very fast to do the geometric corrections. And there is another way, another correction method, different from the warp file. We can find it in there. Warp file as image to map. If we choose this one and input the file need to be corrected, we choose the TM data and press OK. This one, the difference from the previous method is that here we can change the pixel size of the output file, because we know the TM image with the spatial resolution of 30 meters, so we can set the output pixel size with 30 meters, and we need to press enter, so the output pixel size will be calculated automatically, and the warp parameters from this one we may choose the second one as use 2 or 3 degree, and resembling method we also choose nearest neighbor, background set to 0, and this is 30 meters to warped TM 30 meters, press open, then press open. Okay, this is the file be warped with 2 different ways. The first one is warp file, the second one is warp file as image to map. The difference is this one can set the output pixel size, and this one cannot set the output pixel size, and the pixel size of the warped file is the same as the the reference images is the same as the reference images. So we can find the warped file with 30 meters. It has the file images pixel 30 meters, but this one is 10 meters. Finally, we will open the corrected image for comparison, because the comparison is not obvious in Classic in NV Classic. So we will compare it in the NV new interface and close this one. We file, close all file. Want to do this? Yes. No. Close all file. And back to the NV new interface. Close all file. And we open the file before and after correct IS data image correction data image to image, and this is the two file before corrected and we need to choose the file after corrected. This is 30 meters, and this is the warped file, and the warped file has the image to map. Press open and zoom to extent. Okay, find the file information. The warped file have the same projection with this one, with the reference file. And if we find this is the reference spot file, and this is the warped TM file. This is the warped 30 meters TM file. Look, the lake, we can use the portal to compare them. We can right click it and choose load new layers and display the spot images. Okay, can you zoom to extent? In this way, we can find the two images overlapped. The lake is in the same location, but the spatial coverage is different because they come from different sensors, and the different satellites have the different orbit, observation range. Okay, this is the image to image geometric corrections. This is all of the content we are going to learn in this lesson. So, to make a simple summary, in this lesson, we learned the purpose or the function of geometric correction and carried out geometric corrections to three different situations. And the first one is georeference by sensors to correct the modis file. And the second one is to build the ground location table, GLT, to perform the geometric correction. We test it on the Fengyun 3 data. And the third one is image to image registration. We perform it by select the ground control point using NV Classic. As for the last one, correction from image to map, we will talk about this one in the next lectures. So the class is over. Thank you.